We also have a bunch of projects that we might get for this. I actually have to even though I don't really like it. Sorry.
So are you at SEC?
All right, so looking ahead to things we have going on, today we're starting chapter 9. We'll finish chapter 9 on Monday. We'll do chapter 10 the rest of next week. Then there's some, I guess, let me move on to gases. I'm trying to think what comes next. So there's a Mastering Chem due Monday, which by the end of class today, you should be able to do all of it. So if you wanted to get started on it over the weekend, you can easily do most of it. We'll do an individual quiz on Monday. And then we have some decisions to make, because a week from today, right, is Mountain Day Friday, where class you're supposed to be lining up for the parade right when this class ends. So we have to, you do have class on Friday, it's just no classes after 2, which is the class that squeaks under the bar. And so we just need to talk about, because normally Friday is a group quiz. So be thinking of your options. Either you do the group quiz on Friday like normal, and you just try to be fast, or we do the group quiz on Wednesday and then no quiz on Friday. Yeah. And you can, a few yeses, okay. Yeah, I'm gonna let you think about over the weekend. I'll ask you again on Monday what you think the better option is. And I do have all your exams graded. The grades were posted last night on Mastering, so you may have seen it already, but you will get them back at the end of class. So, in general, the class average is like an 85, so I think that made the test too easy.
No. I studied really hard.
Oh, maybe that's it. Everyone studied really hard. Maybe. That could be it. That could be it. You guys surprised me because there were a few hundreds in here. So, yeah. There's a few hundreds and a few 97, 98s where they just missed either a multiple choice question or they forgot their units. Units. They'll get you. So, overall, very pleased. Very pleased.
What was the lowest score?
I think for this section, I think the lowest was mid 60s. So I don't think anybody failed. In fact, no, I can tell you, no one failed the test. So, yeah. All right, so how many people have done Lewis dot diagrams before? Lewis dot structures or Lewis dot diagrams? Okay. That's all right if you don't remember. It's just this is intro to Lewis dot structures, and so if today seems a little boring, hang with me. It gets more interesting, but it's going to be mostly a review if you've already seen it, or maybe brand new if you haven't seen it before. So let's talk about bonds, and then we'll talk about how we use what we know about electronic structure to help us figure out what a bond is. All right, so chemical bonds form because they lower the energy between two, I'm just going to call this 2 atoms. I mean, charged particles is also true, but more generically 2 atoms. So when you have 2 atoms approaching each other, the nucleus of one, right, which is positively charged, is going to be attracted to the electrons of the other atom. Right, they're coming in space. There's the one atom that has negative charge on the outside. It's being pulled in by the nucleus of the other one. But at the same time, right, the other atom also has electrons, and so there's going to be some repulsion there, like the 2 electron groups are going to push each other away. So the formation of a bond is maximizing the attraction and minimizing the repulsion. So bonds are only going to form when you can minimize the repulsion between two electron sets and maximize that nucleus pulling in the other electrons. There's going to be two types of bonds we're going to talk about. We're going to talk about covalent bonds. And then ionic. I'm going to put bonds in quotes. Because when we define bonds, it won't make any sense that ionic is a bond. Wait for everybody to catch up. Okay, let's get this up. All right, so the electrons in the valence shell are the electrons that are available to participate in bonding. All right, where would the valence electrons be found? Closest to the nucleus or farthest from the nucleus? Right, they're the farthest from the nucleus, which means they are closest to whatever atom is coming into them. They're on the outside. When you have a noble gas, right, those are the ones we consider to be completely unreactive. And it's because their outer shell is filled. They have 8 valence electrons coming from a, right there, S2P6 is completely full, so they're not interested in getting any more electrons. But for every other atom, so everybody who's not a noble gas, all right, they're going to have less than full outer shell. There's some combination of electrons less than 8. They're going to reach their 8 electron quota by sharing electrons with another atom. And that sharing of electrons is what we call a bond. All right, so if that sharing of electrons is what we call a bond, you can see here in a second why ionic bonds have to have bonds in quotes. So an ionic bond is where you transfer an electron from one atom to another atom. So if the idea is of sharing an electron is a bond, this is a transfer of an electron. So while your textbook calls it a bond, it's not really the same thing because it's not sharing, it's transferring. So we're going to call ionic bonds, I'm going to put bonds in quotes because it's not the same thing. All right, so let's take a look at sodium fluoride. And my periodic table fell down the other day and no one's come to put it back up. So you're just going to just sitting curled up in the corner. All right, so we're just going to look at my periodic table over here. All right, well, you can't see that at all. Let's see if I can zoom in. Oh, that's a little better. All right, so here's sodium sitting at 11 electrons. So let's look at sodium's electron configuration. All right, so if it has 11 electrons, it's sitting over here in this spot. All right, it's going to be like 1s2, 2s2, 2p6, 3s1, right? And then we can take a look at fluorine. Fluorine is over here, right next to neon. And so that's going to be 1s2, 2s2, 2p. 5. So if these are going to be ionic bonds, right, we have to make ions out of these atoms. So what kind of ion should sodium form? +1, -1, +8, -62, +1. Good. And which electron is going to be the one that is transferred? That 3s1, right? The valence electron. So then what sort of ion should fluorine make? All right, this guy. And where is he going to put that extra electron? On the end, right? He's going to put it right there. So did I add that electron to the valence or to the core? These are the valence ones, right? Because they are all n = 2, which is the largest. So I put that extra electron in the valence, and I took it out of this guy's valence. So when I make sodium +1, that electron's not lost. It's not floating free, hanging out, waiting for the next atom to come by. It's specifically transferring it to another atom. So ionic bond is when two atoms come together and transfer at least one electron from one to the other, and then they're stuck together by charge. So they're not stuck together by sharing electrons, they're stuck together by the fact that one's a plus and one's a minus. So they're stuck together through their charge difference.
So you have to use two different, like a metal and a non-metal.
Yep. Yep. All right, so let's look at my trickier example. Here I have magnesium. Which is, I mean, it's right next to sodium. So what kind of ion would magnesium form typically? +1, +2, -1, -2? +2, right? And which electrons is it going to lose, from the valence or from the core? Valence, right? It's going to lose these two. All right, so we'll take a look at chlorine. All right, how many electrons is chlorine looking to gain? One, and where's it going to put it? Right, in that 3p. So how many electrons did magnesium donate? 2, right? It donated 2, got rid of all 2. How many did chlorine take on?
Well, one per.
One per chlorine, right? Because the chlorine can't take on 2 by itself. So it has to have 2 chlorines each taking on 1. Right, so you have to have MgCl2 because each chlorine can only take on 1 electron, but magnesium is going to give up 2 altogether. And they're still held together all by charge. How do we feel about that? Pretty straightforward? Yeah. So I must have, like, MgCl wouldn't work because magnesium right now is +2 and chlorine is the -1. And so you have to have 2 chlorines and they're each -1 so that the charge balances out. Otherwise you'd have a loose electron floating around wreaking havoc. Can't have that. Every electron has to be associated with somebody. So, yeah? All right, so now we're ready to share electrons. Right, that was transferring electrons. Now we're ready to do some sharing. All right, so covalent bonding is the sharing of electrons between atoms. And we can have a few different varieties of covalent bonding, and we'll start off with a single covalent bond. See what my example is. There we go. All right, so let's look at F2. So let's look at the individual atoms and then we'll figure out how they can share some electrons. So if I have F, all right, that's its electron. How many electrons does it have in its valence shell altogether? Right? If those are the valence, it should have 7 altogether. And back a page or two, we said we'd like them to have 8, right? Everybody wants to have 8, just like we had in the ionics, wherever that just went, right? They went from not having too many to having exactly 8 in their valence, or not enough to having 8 in their valence. And so everybody wants to have 8 in their valence in general. We'll talk about some exceptions next week. In general, everybody wants to have 8 valence electrons. So how can I put 2 fluorines together so that everybody gets 8? So what we're going to do is we're going to draw this as a picture and then put the electrons around it to figure out how can we reconfigure the electrons to get it so that everybody has 8 electrons around them. So a Lewis dot structure starts off by putting the element I'm interested in kind of in its center of the molecule. Then we are going to only show the valence electrons. So there are 7 valence electrons that I need to place around this single atom. And we're going to follow Hund's rule in that electrons pair as a last resort. So I typically start, like I imagine my F has 4 sides to it, like it's in a little box. And so I do 1, 2, 3, 4 electrons. And I still have 3 more to do. So then I go around a second round. And I give everybody a pair so that the least number are paired up as possible. So how many electrons is fluorine lacking? 1, right? So if I drew the other fluorine, because this is F2, and drew it similar, you can use dots or X's or open circles, doesn't really matter for your dots. I need them to form a bond where I'm going to share electrons between the 2 atoms. And by doing that, I can double count the electrons. Now I'm going to count them being on fluorine number 1 and fluorine number 2. So I'm going to redraw this. You could just kind of do a different picture if you want. But so I'm going to draw it like this. Yeah.
Would you accept with the one you originally drawn, which are open circles where there isn't one? Would you accept
That's
that?
fine, yeah.
Okay.
As long as it's obvious what you're trying to tell me. All right, so if I draw it in this manner, I now have 8 electrons around both atoms with the ones in the center being double counted. So these ones in the center are the ones representing my covalent bond. Right, it's a pair of electrons being shared between the 2 atoms. So that has to be a covalent bond. And then now I have 8 electrons around this one, and I have 8 electrons around that one. So it's a way of getting around not having enough electrons. All right, I wrote really big. I'm going to flip my page over. We're going to do another example. So, single covalent bond continued. Let's say I have a molecule that has more than 2 atoms, which is like 99% of the chemistry world. Something with more than 2 atoms in it. We'll start off with this guy, old favorite, water. All right, so if I had H2O and I truly didn't know how the H's and O's were connected together, which you may not know, there are some guidelines as to how do you decide how they're hooked together. All right, so when drawing a Lewis dot structure, these are the in general guidelines you want to use. So we're going to place the least electronegative atom in the center of the molecule. Unless it's hydrogen. Hydrogen has its own rule. So put the least electronegative atom in the center. Hydrogen is always terminal, or terminal meaning on the ends. Right, so you're either in the center or you're on an end. You could be, there's some cases we'll have some stuff in the middle, but terminal meaning hydrogens are always on the end. Calculate total number of valence electrons and distribute them so that every atom has 8. Unless it's hydrogen. And we'll talk about why hydrogen's weird instead all the time. All right, so those are going to be the 3 overreaching guidelines that we're going to use to figure out how to build a molecule. All right, so let's take a look at water. Let's first do the electron configuration of oxygen. All right, so oxygen, I don't know where I have my periodic table. Here's oxygen over here. All right. And so it's going to be 1s2, 2s2, 2p4. What's the electron configuration of hydrogen? 1s1. And we have 2 of those. All right, so now we can talk about why hydrogens are the exceptions to all these statements. Does hydrogen want 7 more electrons? No. How many does it actually want? It wants 1 more. It'd be happy with 1. Either it's going to lose 1 or gain 1, right? It's either going to become H plus or it's going to get 2 and have a full S. And so hydrogens always have to be on the end because they can only accept 1 more electron. If you put them in the center of a molecule, they don't have any, they can't make 2, like it's like they're an amputee. They only have 1 arm to reach out. They don't have 2 arms to grab other molecules. They can only do this. That's a problem. YouTube, I'm sorry, that's a terrible example, but that's all I could think of. And then looking at your periodic table, right, hydrogen is kind of an exception to electronegativity in that it's probably just about always going to be the least electronegative thing in your molecule, right, being all the way over here compared to F. But we just say you can't put H in the middle. And so rule number 1 says put the least electronegative excluding H. H can never go in the center. Always has to be somebody else. All right, so we're starting off with a molecule that only has O's and H's. And so obviously the O goes in the center. And I'm going to put these guys terminal, meaning they're on the ends. All right, so calculate the total number of valence electrons and distribute them. How many valence electrons does oxygen have? 6, right? So that's 6 valence. And this is 1, and this is 1. So what trips people up a lot using Lewis dot structures is just because you came with 6 electrons does not mean you get to keep those 6. It's kind of like coming to a potluck, right? You brought your bag of chips to the potluck with the intention of sharing them with others. You didn't bring the bag of chips just to sit in the corner and eat your bag of chips. I mean, maybe you did. That'd be a terrible potluck guest. Which I understand. Nobody your age goes to potlucks. But maybe you've been to one at some other point in your life. They become trendy again when you're old, like me. You don't want to make dinner. And so you guys, well, I'll just make something. Anyway. So, if you can think of a better example of how you bring something but you don't get to keep it, you share it with others, use that example in your head. So we're going to count up the total number of valence electrons. In this case, there are 8 total. And we're going to redistribute them so that everybody gets, all the atoms who want 8 get 8, and hydrogen gets 2. So it is a pretty easy one in that we can see, right, if we do this, is hydrogen happy in this case? Right, it has its 2 close to it. How many electrons have I used up? I used up 4, so I have 4 more to go. And I'm going to put them around the oxygen. Does the oxygen now have all the electrons at once? Hydrogen has all the electrons at once. How many covalent bonds have I made? 2, right? This is a covalent bond, and that is a covalent bond. We're going to do lots more examples, because this one seems really easy. It is. They get trickier. All right, so let's talk about what these guys are here and here. So you can either redraw it, talking about lone pairs, or you can just refer to water as your picture. I'm just going to go ahead and redraw it. All right, so this is covalent, that's covalent. These guys right here, these sets of electrons that are not participating in a bond, are called lone pairs. They are super critical to the chemistry of the molecule, so you can't ignore them. But they are just the electrons that are not actively participating in bonding. Right? What if I got rid of those lone pairs? Would oxygen be happy? No, it would be catastrophic. Water would be blowing up everywhere. So we have to have them, right, so that everybody has their octet around them. But they just mean they're not participating in bonds. How many lone pairs do I have? I have 2 pairs, right? So I have 4 electrons, but I have 2 lone pairs. All right, so we're going to talk about lone pairs a lot in this chapter and the next chapter, because the lone pairs actually force the geometry that water sits in. So lone pairs are the things that force water to have a certain shape in 3-dimensional space. So it's pretty neat. All right, questions so far? Good? Okay. I don't know which way I was going with my notes. Maybe this way? No? No? Oh, here we go.
Is love here? make a shape of all molecules or just water?
All molecules. Lone pairs are one of the deciding factors as to what three-dimensional shape water has, or any molecule. All right, so that was great if we had just one lone pair, pretty straightforward molecule. But we may also have multiple bonds. So atoms can share more than one electron pair. All right, and this is going to occur when you need to have 8 electrons around an atom. But single covalent bonds do not account for all the valence electrons available. All right, this will make more sense if we do some examples. So let's take a look at C2H4. All right, first thing we need to figure out is the number of valence electrons available to us. And so eventually you'll get to the point where you don't have to write out the electron configuration every time, but we're just going to do it the first bunch of times just to get the hang of it. All right, so those are the 2 atoms available to us. How many valence electrons does carbon have? 4, right? And oxygen has 1. If I have 2 carbons, how many valence electrons do I now have? 8, plus I have 4 hydrogens, so how many total valence? It'd be 12. All right, so I have 12 total electrons to redistribute. All right, let's take a look at carbon and hydrogen. Which of those 2 atoms should I put in the middle, the carbon or the hydrogen? Carbon. Can I tell the difference between the 2 carbons? Right, would carbon have any difference? Okay, so they're going to sit next to each other. All right. Well, I know the carbons are bonded to each other. And then what do I do about those hydrogens? Do I stick them in the middle here? Do I put 2 hydrogens next to each other? I'm going to put them on the ends, but I have 4 of them, so I'm going to do something like this. All right, I have 4, and they all have to go on an end, so I put 2 on each end. Have I used up all the electrons I brought to my potluck, my electron potluck? I've used up 2, 4, 6, 8, 10. I have 2 issues. 1, I still have leftover electrons. 2, does this carbon have 8 around it yet? What about this guy? How can I fix that? I've got two more in here, which we're in the multiple bond section, so that should have been kind of a giveaway. It's going to have more than 1 bond. All right, so now looking at are my hydrogens happy? Are my carbons happy? Are you happy? All right, you can also, once we get to this point, right, I'm going to circle this, all right, this is the covalent bond. And in fact, the name's kind of a giveaway. That's a double bond. meaning that I have two sets of electrons that are being shared equally. All right, you ready for like one more level of challenge? Okay. All right, let's say I have N2. So looking at N2, right, N is right here in my electron configuration. Question. All right, and I have how many valence electrons first? 5, right? 5 valence. So how many total valence should I have to redistribute? 10, right? I'm going to have 10 valence. And because I only have 2 atoms, they're obviously going to be stuck to each other in some sort of way. I'm going to say when you do these problems, I recommend doing them in pencil because it's going to be a lot of trial and error where you try out a combination and be like, oh, that doesn't work. Then you erase some electrons, move them around, erase some more. Unless you're a brave person with lots of paper and want to do it in pen, I recommend pencil. All right, so let's say I got my 2 here. All right, so it needs 8. How's that looking? Way too many. I need 14 electrons to do it like this. All right, what's one way I could solve that? To get everybody have 8, but use less electrons. You're right, I'm just going to do it baby steps. All right, so let's say I want to try a double bond first. Is that better? The exact same? Exact same badness? I'm going to make a triple bond. So these are going to be I have a few more practice ones before we end class today, but these are going to be ones that you're just going to need to practice. You know, write out this weekend, since there's officially no homework, like you can certainly get started in mastering, but there's also, I have a Lewis.structure practice worksheet on my class website that if you want to just kind of go through and has the same rules, you can just kind of do some practice and just figure out how to make it work.
Is there a limit to how many bonds you can have?
I have never seen anything with more than 3.
Okay.
Theoretically, you could have 4, but not in this class, if that's a good luck then. All right, let's do one more practice one. Let's do this. Let's do a challenge problem. I think you guys are ready. Let's do some carbon dioxide. Okay, we've had both of these before, so. All right, so how many valence electrons does carbon have? 4. You'll get to the point that you just know. Carbon 4, oxygen 6, fluorine 7. So if carbon has 4, oxygen has 6, how many total will I need? 16, right? Because I have 2 oxygens, so that'll be 12, plus another 4 will be 16 total. Looking at carbon versus oxygen, which is the least electronegative? Carbon, right? So we're going to put carbon in the center. And put oxygen on either side of it. All right, what if, let me try this. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 8. 16 electrons.
Wait,
Yeah.
C, these are both the molecular atoms, right, or molecules, whatever, where they have the C2 and O2, right?
It's O2, not C2.
C, not one?
All right, so here is my first attempt at the structure. How's that looking? What is wrong with it? Oxygen doesn't hit, okay. If I had a pencil, I'd erase it. I don't have a pencil. All right, so what's some way I can fix that? Yes, I'm going to put some double bonds. Right, I'm just going to move these electrons over. Now, does oxygen have its full 8? What about carbon? Is that happy? Yes. Good, good. All right. You guys want to do one more? Sure. Why don't we try? What do I have in my challenge problems? Can't pick up that one. Okay, let's try this. Alright, so I got Ni3. It's much easier to be active. That's why I keep writing down the electron configuration for you. I'm hoping they're going to put it up soon. Oh, let's see. Okay, 1, 2, 5, that's 2, 4, 10. So this is where it's going to be both intuitive and counterintuitive, right? So iodine is over here in the halogens. So does iodine want to get one more electron or lose one electron? Right, it wants to gain one. So looking at its electron configuration, while the 4d10 is sitting in there, we only look at the 5s when we count valence. So iodine will have 7 valence. Which is where I disagree with mastering in counting valence. Because if you count the D's in valence, you'd have the wrong number of electrons. So the D's do not count when we're counting up valence electrons. Yeah. Mastering they do, which I don't understand why, because it's confusing. It's not. It's fine if they did that, but we need to count only 7 when we do this. So it's just 7.
Both of those are molecular, right?
Yep. All right, so then how many valence would nitrogen have? 5. All right, so we're going to 5 plus 7 times 3. So 21, 26, right? So we have 26 valence electrons to put everywhere. Which is the less electronegative, the N or the I? This one's a little tricky. Actually, let's think about it this way. How many electrons does iodine need to gain to get to its octet? 1. If it only needs 1, how many bonds can it make? Each one can only make 1 bond, right? Because it can only share 1 more electron with somebody. So would it work if I put that in the center? No. It only works if I put nitrogen in the center and put the iodines around it, right? Because iodine is coming with 7. So how many, I guess nitrogen's coming with 5 more. So how many bonds can it make this way? How many covalent bonds can it make? right? If I put one here, one here, one here, how many bonds is that? 3, right? 3 bonds. Are the iodines happy?
Yes.
Is the nitrogen happy? And have I used up all my electrons? Right. So where do I put them? On top. So how many lone pairs all together does this molecule have? Nitrogen has 1, but all together it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 lone pairs. We're going to do this all day Monday also. So if it's, I would say definitely do the worksheet over the weekend if you have time. At least look at a few of them. And maybe try the mastering, because the mastering has a tutorial as to like how do you click atoms and make it do the little bonds and lone pairs and whatnot. And we'll do some more on Monday. So for your tests, I got them all graded, but they're not alphabetized. Sorry, you get really one or the other. So is that okay? So there's apparently no particular order. So I don't want the test back. Take it with you, study from it for the final. I have no need for it. And then when you get it, you're free to go. So let's see, I have Sarah. Okay. Lily? Lily, okay. Can I call you Sarah? Yes. All right, Lori? Caitlin? Lauren? Oh. There's 2 Laurens with a B. Perfect, yeah. Perfect. There you go, Brittany. Clayton. Drew. Erica. Derek. Mandy. Andy, Kayla. Kayla. Yeah. Rebecca. Oh, sorry. You too, Melissa. I'm going to be one. Jasmine. Daniel. Nita. Yeah, right. Melissa. Kenzie. Maggie.
So we can continue about this.
Lexi. Eden.
Praise the Lord, it's the best grade I've ever made.